Hello viewers, in this video we are going to learn about as a part of first law of thermodynamics we are going to learn about heat capacity. I would like to give you some shortcuts here. What is heat capacity? It is the amount of heat that is commonly required to raise the temperature of the system, that is equivalent to 1 kilo or 1 degree centigrade. Now, heat required, heat capacity of substance. If you take heat capacity at a particular temperature, heat capacity of a substance, right? It is m grams. Why? Because grams are indicated by m, right? Mass is given by, it is going to be given by, right? C equal to heat capacity Q by delta capital T temperature, that equal to Q by very important equation T2 minus T1 units. Okay, joules for uh, and also or kelvins. We can take K, right? Heat capacity. Let us take same heat capacity I am taking here. Heat capacity of 1 gram substance is called specific heat. What is that called? Specific heat or heat capacity, specific heat capacity. Specific heat capacity is indicated by CSP. Specific heat capacity, right? Or it is also indicated by S. Now, specific heat capacity CSP is equal to C by M, right? Q by M delta T, right? Units I am mentioning here, let us take out them. Along with that, heat capacity of 1 mole, let us take heat capacity. Heat capacity of 1 mole of a substance is called molar heat capacity. These definitions are very important. The molar heat capacity is indicated by Cm, right? Like Chief Minister. Now, Cm is equal to molar capacity Cm and then CSP, right, is nothing but into M. Let us take capital M here equal to Q into M by M delta T, right? As you know very well, the Cm or C by M equal to Q by M delta T. Same thing I am taking here, right? Here Cm is equal to nothing but molar capacity is equivalent to specific heat capacity into M, right? Right, that is equal to Q into M by M delta T. Same formula I wrote here. The value of Cm value I mentioned it here. And if you do the cross multiplication, I got this equation at last. Now finally, that is equal to Q by N delta T is equal to C by N. N is nothing but number of moles. So what is M here? The equation whatever I wrote, this is the total equation for heat capacity equal to, this is the equation for capacity of a heat. Capacity of a heat. Now M is equal to molecular weight of a substance. Molecular weight of a specific substance is going to be taken by M. N is equal to, already told you, number of moles of a substance. Here N is there, no? N, number of moles of a substance. Small m is equal to mass of a substance. Capital M represents a molecular weight, but mass of a substance is indicated by small m here. Right. At last, when CSP is large, if CSP, specific heat capacity, when CSP is large, if it is large, what will happen in a given amount or in a given specific amount, in a given specific amount, whatever heat is results in only small temperature rises. If Cm at a constant, if Cm at a constant V volume, constant P, nothing but pressure, respectively R. Cv and Cp value. Cp minus Cv is equal to R. Okay. That implies Cp is equal to delta H is by delta T, right? At last P. And the Cv is going to be equal to delta U by delta T into V. Now, where delta H is equal to, in the Cp value, if you take this Cp value, delta H is equal to Qp and delta U is equal to QV. Now, the point is for liquids and solids, if you take the liquids and also solids, how these values are going to be changed? Cp is equal to always Cv. But for gases, but for all kind of gases, Cp is greater than the Cv. According to Dulong, a scientist called, if we take a great scientists who are involved here, according to Dulong and Petit's rule, Dulong and Petit's rule, right? Atomic mass of a solid element. If you take atomic mass of a solid element, atomic mass of a solid element is equal to 6.4 by specific heat, except the this value is except there is an exception for beryllium, boron, and also silicon. Reason we will learn it later on. It is a broad topic. Cp by Cv is equal to, as you know, this Poisson's ratio. I'm talking about lambda Poisson's ratio. Poisson's ratio can be mentioned like that. Okay. Lambda value depends upon the atomic number or atomicity of a particular gases or molecules. If I take the lambda, it is going to be depends directly upon the shortcut I am writing here, atomicity, as well as molecules, number of molecules that are present in them, to a degree of freedom, right? As well as rotational energy in case of translation energy in case of diatomic molecules and polyatomic molecules. So this lambda value also depends upon vibrational energy, vibration, when a vibration occurs, how much energy produced. When the rotational, when an object is rotating, energy is going to be produced, how much it is produced. Translation energy, when an element is translated from one form to another form, how much energy is going to be produced. Diatomic energy, if the atoms are uh, combined together to produce a specific energy, diatomic energy, and polyatomic energy. If a number of atoms are added, combined, joined together as a single unit to produce the energy, that is polyatomic molecules. These factors also generally defines the lambda value. Now, the value is equal to 1.66, right? In case of the gas, in a monoatomic structures like hydrogen is a monoatomic structure, helium is there, neon is there, argon and krypton also there. Got my point? Now, hydrogen cannot be included here. Reason I will tell you later. Okay? Only I am taking helium. In case of same symbol equal to, if it is 1.40 and the gas is diatomic, the gas is going to be diatomic. Example for this diatomic structure: oxygen, nitrogen, chlorine, hydrogen, etc. If you take this structure 1.33 for polyatomic structure, example for polyatomic structures, right? CO2, SO2 is there, K2O2 is there, O3 is also there. But especially this simple value for monoatomic structure, how much it will be there? Mono, single atom in a gaseous state. Cp is equal to 5R by 2, or Cv value is equal to 3R by 2. So for monoatomic gases or in a gaseous state of monoatomic structure, Cp value is 5R by 2, Cv value is 3R by 2. Clear my point? At last, for diatomic gases, for diatomic gases, Cp value is equal to 7R by 2, Cv value is equal to 5R by 2, right? But if you take a triatomic structure, tri means 3. Triatomic gases, Cp value is equal to 4R and Cv value is equal to 3R, right? So this is the brief description upon the heat capacity. In the next video, measurements of delta U and delta H in the calorimetry, how it is going to be measured, I am going to explain in the next class. Thank you. Have a nice day.